Today we will be discussing the extra credit lecture for our gas laws unit. The extra credit lecture is based off of a concept that you have already learned. Earlier in our unit we discussed determining the molar volume of a gas when the water levels were equal. In other words, there was no difference in the level of water inside the gas collection tube and inside the beaker in which the tube sits. You also did this in your lab. You remember you were able to take the gas collection tube over to a large graduated cylinder and move that gas collection tube up and down until you got the water level inside the tube and the water level in the graduated cylinder equal before you measured the volume. To add another layer of complexity to this problem and to make it more realistic, we are going to then fix the gas collection tube so the gas collection tube cannot be moved. Therefore, the likelihood of the water level matching from the inside of the tube to the beaker that the tube is sitting in is that those will be exactly the same is very, very unlikely. We'll start our problem today by drawing a complete diagram. We'll have the gas collection tube, a very long, skinny tube that is placed inside a beaker. That beaker contains a water level, and it's very obvious in the problem that they talk about the water level in the tube is 5 centimeters lower than in the beaker in which the gas collection tube is sitting. So I drew that in red with a couple of lines to show the difference there is 5 centimeters. The second part of problem A says to identify our variables. The first variable that we will pull from the problem listed above is the volume of our gas at room temperature and pressure. We're going to label that as V sub 1 or V1, and we're going to write that as 35.4 milliliters. Next thing is our room temperature, which we will label T1 is 25.0 degrees Celsius. That we will immediately convert into Kelvin, and we have 298 Kelvin as our initial temperature or our room temperature. Then lastly, we have our P1, which is our initial pressure or our room pressure, and that value is 604.2 millimeters of mercury. That is the room pressure. In other words, that pressure is being exerted right here on the surface of the water in our beaker. Okay? Now, the issue is that that pressure is being translated through water and then exerting a force on the gas trapped inside the tube. We need to then go ahead and use the water vapor pressure at this temperature of 23.8 millimeters of mercury, and as you have done with the previous problems, subtract that from our P1. So we will subtract 23.8 millimeters of mercury as that air pressure is then exerting a force on the water, which then exerts a force on the gas trapped inside the tube. Now, the other issue that we have to deal with at this step is the fact that these water levels are not equal. They have a 5 centimeter difference. We need to convert this centimeters of H2O into millimeters of mercury. Since our pressure readings are both millimeters of mercury, we need the units to match up. We'll have a two-step conversion problem. We start with the 5.00 centimeters of water, and ultimately what we are trying to get to is some value with a unit of millimeters of mercury. First step of the conversion is easy. We need to go from centimeters to millimeters. That's something you've known since August. For every 1 centimeter, we have, well, it would help if I wrote it right, 10 millimeters of H2O. Now, the second step of the conversion is where the densities that are listed up above here are going to be very helpful for us. The density of mercury is 13.55 grams per milliliter versus the density of water being roughly 1. In other words, the density of mercury is roughly 13.55 times the density of water. Now, why that's important to us is because these objects will exert different forces on the trapped gas. Another way of thinking about it, if I had a column of mercury that measured 1 millimeter of mercury, this column will exert a force in that direction. it would take an equivalent column of 13.55 millimeters of water, whoops, excuse me, of water, H2O, to exert the same downward force. And I realize my columns aren't exactly the same width. We'll ignore that sloppy artwork for just a moment here. So if it takes 13.55 millimeters of water to exert the same force as 1 millimeter of mercury, we can use that as our conversion factor here to get to the millimeters of mercury. 13.55 millimeters of water will exert the same force as just 1 millimeter of mercury. So we go ahead and do that math there. You see the way I have the problem set up, that the units cancel each other out, and we ultimately get the unit that I'm looking for, and we get a difference here of 3.69. So that's the last issue that we have with our initial pressure. Now the question becomes, do we add that difference or do we subtract that difference? And that's when you come back to this diagram and you determine, do I have a higher pressure, atmospheric pressure or room pressure, or do I have a higher pressure inside the tube? Well, you look at the levels and you see that the water level inside the tube is lower than the air pressure, therefore the pressure inside the tube has to be greater. It's exerting a greater force on the water than the atmospheric pressure is. So if we're trying to find the pressure inside the tube, and that's the larger of the two, we are going to add this difference here to get our final answer. So we're now ready to go ahead and get an answer for P1, which I calculated to be 584.1 millimeters of mercury. So we've identified our variables, drawn a complete diagram of this experiment, and really dealt with the most difficult part of this problem, which is identifying how to handle and translate the difference in centimeters of water to millimeters of mercury. As we go through the rest of the problem, what you'll see is the rest of this is pretty much review over how to do, regardless of whether the water levels are equal or unequal, the rest of the problem here is pretty much the same as the problems that you have already done. So, calculating the number of moles of H2 produced. We start with the 42.3 milligrams of sodium that were given to us in the problem. We ultimately want to solve for moles of hydrogen gas here. So first step, we go ahead and do 1,000 milligrams in 1 gram of sodium. Then the next step is to go ahead and convert from grams to moles, go from the left part of the mole map into the center, dividing by the 22.98977 grams per mole, which is the average atomic mass listed for sodium. Then the last step, we're going to use the balanced chemical equation from above. We've got for every 2 moles of sodium, we produce 1 mole of hydrogen gas. So we'll have 2 moles of sodium for every 1 mole of hydrogen gas. Unit-wise, milligrams cancel with milligrams, grams cancel with grams, moles cancel with moles, and we end up with the unit that we are trying to achieve. When I do this calculation, I get 9.20 times 10 to the minus 4th moles of H2. Now, part C, calculate the volume of H2 gas at STP. We have identified in the diagram, part A, T1, P1, and V1. So we know that we're going to use the combined gas law here. We're going to have P1 V1 over T1 is going to equal P2 V2 over T2. Now I'm going to rearrange this equation so I isolate V2, since that's what I'm ultimately trying to solve for. I'll have P1 V1 and T2 over T1 and P2, which equals V2. And that's my rearrangement. Now there are 2 more variables that I need to identify here. I need to identify obviously P2 and T2, which are both standard temperature and pressure. P2 is 760 mmHg and T2 is the 273 Kelvin. So now that I've identified all 5 of the variables, I can bring this equation over here, V2, my P1 given to me in the upper part of the problem is the 584.1 millimeters of mercury. Then my V1 is the initial volume, 35.4 milliliters of hydrogen gas produced. And then the T2 is standard temperature, 273 Kelvin. Then I have my initial temperature, which was 298 Kelvin, listed at the top there, times my pressure at standard conditions, which is 760 mmHg. Unit-wise, we get millimeters of mercury canceling with millimeters of mercury, Kelvin canceling with Kelvin. So we're going to have V2, and that's going to equal a certain number of milliliters of gas. And when I do that calculation, I get 24.9 milliliters of hydrogen gas. Now, part D, what is the molar volume of the gas at STP, liters per mole? I take my answer from C. I'm going to convert that from milliliters to liters. 24.9 milliliters is going to be 0.0249 liters of hydrogen gas. Then I'm going to go ahead and take that and divide it by the number of moles I got in the previous step, 9.20 times 10 to the minus 4th moles. And I get a final answer there of 27.1 liters per mole. We know, we've talked about it multiple times at this point in the unit, what that number should be. The molar volume of a gas at STP comes from our discussions back in December with the mole map, that value should be 22.4 liters per mole. So the last step we have to do is calculate the student's percent error. Okay, percent error is always the absolute value of the experimental minus the accepted divided by the accepted times 100. So I'm going to have 27.1 liters per mole minus the accepted value of 22.4 liters per mole divided by the accepted value of 22.4 liters per mole. And then we take the absolute value of that times 100. And when I did that calculation, I got 20.9% error there. In an ideal world, we get a 0% error because we've got the true molar volume of a gas of 22.4 liters per mole. If you have any questions, please contact your teacher during ICE.